In this session, we will focus on the introduction of monaural, that is a single-channel speech denoising techniques. Traditional single-channel speech enhancement methods use more knowledge of digital signal processing, both in time domain and frequency domain. Mainly in frequency domain processing, like the traditional spectral subtraction method. There are also some methods to combine time and frequency analysis. Adaptive filtering has been used for speech denoising in time domain. Optimal linear filtering has been used extensively for speech enhancement, including Wiener filter, Kalman filter, and other statistical methods. Linear filtering methods originate in stochastic processes, while subspace methods have largely been based on development in numerical linear algebra and metric approximation theory. Among the single-channel methods, there is a subspace-based method that has also attracted attention, which makes use of the irrelevant of speech and noise signal with eigenvalue decomposition or singular value decomposition. However, because of its relatively high degree of calculation, it is not widely used in engineering. The speech enhancement method based on machine learning is different from the traditional digital signal processing method. It draws on the idea of machine learning and realizes speech enhancement through supervised training, such as DN-based speech denoising methods. The simplest and most widely used enhancement method is spectral subtraction, in which the power spectrum of the estimated noise is subtracted from that of noisy speech. As is shown in the algorithm flowchart, the estimated clean signal is obtained by subtracting the noise signal from the acoustic noisy speech, and the square of the amplitude spectrum of the pure noise is subtracted from the square of the noisy speech amplitude spectrum. Then, the original speech spectrum amplitude is estimated. Finally, the enhanced speech is obtained by IDFT through borrowing the phase of the noise. In order to estimate background noise, speech enhancement techniques typically assume that background noise is stationary. That is, its spectral properties do not change over time, or at least are more stationary than speech. In real applications, spectral subtraction method has simple principle and only needs one microphone. It can be realized with low complexity and easily implemented in hardware. Spectral subtraction methods need to estimate the short-term power spectral density of background noise based on that of the noisy speech signal. Thus, this method often needs silent and voice judgments. In the case of large signal-to-noise ratio, the use of short-term average energy and other parameters can achieve good results. As the method requires a stationary noise when the noise characteristics change. The noise reduction effects may be worse. Then, it needs to pick up the noise characteristics again. This method may lead to some music noise which degrades the voice quality. The adaptive filtering method, also called adaptive noise cancelling (ANC), needs to know the noise of pure speech in advance, and then use the stochastic gradient descent method to approximate the optimal solution. In most cases, prior knowledge such as noise or pure speech cannot be obtained, which greatly limits the application of adaptive filtering methods. However, this method has a wide range of noise reduction application in mobile phone calls. Usually, a noise reduction microphone is used in mobile phone to collect noise in the environment, which is used as a reference input to achieve noise reduction. The adaptive filter can effectively track the input time varying signal in an unknown environment and to optimize the output signal, so it can be used to form an adaptive noise canceller. In the method of ANC, main input signal Xn is mixed by the useful signal Sn from the voice and the other irrelevant noise signal D0n. The reference noise signal D1n is relevant with D0n. Then D1n is processed by ANC, which generates another noise signal D'0n, relevant with D0n. Thus, the main input signal Xn minus the output of ANC to get the output signal S'(n). There is an error signal En between the clean speech Sn and the estimated speech signal S'(n). The optimal output will be obtained by making En as small as possible with LMS, least mean square criterion. The parameters of ANC will be adjusted according to the input and reference signal. ANC algorithm is realized in time domain, while spectral subtraction is a kind of frequency domain processing method. In order to get better results, ANC and spectral subtraction could be combined with time frequency analysis. Wiener filtering is an optimal estimator based on the minimum mean square error MMSE criterion for stationary processes. It also assumes that the noisy signal is the mixed result of speech signal with additive noise signal. Speech signal and noisy signal are both short-term stationary random processes. Wiener filter recovers the expected signal from the observation signal, which is convoluted with the impulse response of a linear filter obtained by MMSE. Generally, the filter coefficients of a Wiener filter are fixed for each frame, while ANC filter coefficients are updated. Wiener filtering is a method of filtering speech signals mixed with noise used to correlation and spectral characteristics of a stationary random process. It has different solution methods. The time domain solution of the Wiener filter is just to solve Wiener-Hopper integral equation. Frequency domain solution of the Wiener filter is to estimate the targeted speech in the power spectrum. According to whether to use future information to estimate the current value, it can be divided into a causal system and a non-causal system. In the research of speech enhancement, there is a special problem with acoustic echo in communication. That's to say, in the course of the phone call, people will hear their own voice in a certain short delay. When dealing with bidirectional voice, the user at the near end has two devices she is dealing with. The microphone used to capture her own voice. The speaker used to convey the sounds from the remote participants of the call at the far end. The problem begins when the microphone captures not only the person speaking locally, that is the voice at near end, but also the voice coming out of the speakers, the transmitted voice from far field. Along with the voice reverberating from artifacts in the room and the walls themselves, this is known as acoustic echo. This acoustic echo is something that has to be cancelled in calls, especially when this takes place without headsets. In a duplex call scenario, the sound from the far end through the speaker needs to be eliminated by acoustic error cancellation, AEC. Otherwise, the microphone collection and the near-end speaker signal are mixed and transmitted to the far end, and the far-end person will hear his own voice. This kind of echo experience is fatal for some communication devices. Acoustic echo cancellation, AEC, is important for speech and audio teleconferencing when simultaneous communication or full duplex transmission of speech is necessary. It has been built into most VoIP solutions, including WebRTC. The goal of AEC is to remove the far-end echoed speech signal from the microphone signal so that only the near-end speech signal is transmitted. The common methods of echo cancellation are as follows. Use different adaptive filtering algorithms to adjust the weight values of the filter and get an echo estimated path to approximate the true echo path so as to obtain the estimated echo signal, and remove this signal from in the mixed signal of pure speech and echo to achieve echo cancellation. That's all for this session. See you next session.